topic of today is trying to see if we can leverage some of the experiences we've had over the past 40 years in oil and gas and leverage them to help with, in particular, well, offshore wind, but in particular floating wind. And I guess if I was to be honest, the situation we see ourselves in now in floating wind reminds me a lot of the early 90s when I was in Aberdeen, and the industry was moving from everything being a fixed jacket platform to floating facilities, and we ended up with some wild and wacky ideas like the Banff FPSO, the ramform shaped FPSO, which had a pitch natural frequency just at the natural, the peak natural frequency of the wave environment, so it wasn't very stable. It was a 5-legged semi-submersible on Buchan. So, a lot of ideas and innovation trying to find the right way forward. We're in a similar phase now. And what have we, I guess over the past 40 years, there's been, a lot of evolution into more and more hostile waters, deeper waters, a lot of focus on supply chain and how to keep that going during the downtimes, innovation, collaboration, and automation, and maybe digitalization more recently. So I guess from a floating wind perspective, where do we see our role? Where does Wood see our role? You can read all the script on there, guys, but to me, it's really about being the integrator. So the engineer or the integrator of the solution. And I think another really important point to take is that society has changed irrevocably over the past 18 months. So this concept of the social license to operate has really come into the consciousness. So anytime, it's real and present as an issue with the fossil fuel industries. And I know this is renewables, but it's still the same onus on us to look at the total cost of a development and returning that environment, that sea, back to the original state when everything is finished. So yeah, look, I think, guys, yeah, we have to look at this thing holistically, and from blue to blue is the expression that we may use. So in terms of the challenge, look, what I'm presenting here is some extracts of work we did in the UK, and it was looking really trying to, the whole idea is that the UK government is trying to understand when will floating wind be subsidy free. So, this is approximately the cost of per megawatt hour for floating wind, just, basically now. And then what are they basically ran a whole load of different scenarios to see where could you get to the cost of the energy being basically lower than, the cost of the energy basically being low enough so that it's subsidy free. And in the UK, there's a big drive for decarbonisation. I think they're targeting, they have already achieved 70% reduction. So to do that, the first thing you need to do is develop a cost model. So we've worked with developed a cost model. We looked at a few different scenarios around the North Sea, and we used the RHI or Ryder Hunt to help us with the modeling and the full life of field modeling. And you can see, first of all, that the breakdown that we're coming up with is approximately 2/3 OPEX, 1/3 CAPEX, and a small little bit for DCOMEX. I guess the relatively small DCOMEX is relative to oil and gas, is that there's no plug and abandonment required. You really just pulley up the anchors and taking away for recycling or repurposing. That just gives you a little bit more detail there on the CAPEX and the OPEX, the different components, installation, a little bit of planning and development work up front, ops and maintenance, and the different components there. I'll just read out a little bit about the base cases. Yeah, 9 different zones around the North Sea, water depths ranging from 75 to 100 meters, mean annual speed around 10 meters per second, mean annual significant wave height just under 3 meters. And then, of course, the anchor type and the mooring line lengths, they're all dependent on the water depth we were looking at. And then transmission system to shore was dependent on the power capacity of the facility, and also the distance to shore, and optimizing to, yeah, so, and basically taking into account your proximity to the grid. So there was, you know, there's quite a lot of work that went into this. It's not just a nominal location. There was a whole load of actual physical locations modeled, and then you know, an aggregation of the costs. Why am I showing you this? Just to show that there is a level of sophistication in the work that's been done. And then the next step we did was we ran what's called a Colab, or, you know, basically it's collaboration. So it's a collaboration workshop. And basically the idea here is we're basically, this was internal, so we're getting internal wood folk to help to see where may we, what are the aspects of cost that we could attack that would help us to achieve that target reduction of 65% in CapEx and 30% in OpEx. So here is the list of areas that we're focusing on. I'm not going to go through all of them, but it's just trying to show that at the end of the day, there is not one silver bullet, which I guess won't surprise any of us. There's no silver bullet that solves the problem. It's a series of incremental improvements that helps to just chip away at that overall life cycle cost of energy. Looking at this slide, I can see there's a lot of information on here, but this is basically the base case for all of the work that was done. So we have to have some sort of a base case. This is the base case: 25-year design life, European manufacturer, 15 megawatt, 33 turbines. And then you can see that there is a significant level of cost reduction depending on the sensitivities that are deployed, like, you know, significant reduction in vessel rates, fabrication costs, installation costs. What's this trying to show? Basically, that you need a multitude of increments to help you get to something approaching the cost of fixed wind. In terms of system design, I guess you can see, I love this diagram here in terms of the level of the level of increase in terms of magnitude of your turbine system, or your turbine system. So what surprised me was that you don't get a huge increment in the as you go from 15 megawatt to 20, which is in the future. You don't get a significant increase, or sorry, a significant reduction in the cost of your energy. And I guess the risk there is that you have, you know, you're going to, the bigger you go, then the more specialized your construction facility needs to be, the more specialized your installation scenario and vessels need to be. So it's it's not necessarily the case that you just go bigger and bigger and you solve the problem. The capacity factor, it's a new concept to me. So the capacity factor is really the amount of wind energy that you yield from a particular location. And I guess a capacity factor of about 50% is a reasonable base case to have. And I guess well, how do you increase or improve the capacity factor for a particular given field? One of the more efficient ways of doing it is having a better control system in place. So you can control the pitch of your blades, and that impacts when they kick in and when they kick out. So you need a certain amount of wind to get the turbine moving, and then you have to keep the turbine. You have to control the blade so that your turbine doesn't spin at too high a rate. So if you can optimize that for each location, and then the second thing is if you can adjust the attitude of your turbine so that you minimize the impact of the turbulence on your downstream turbine, that's how you can improve and increase your capacity factor. In terms of another system design is looking at longer design life. I guess the longer your design life, that's what we see in these mega gas projects in Australia. It's a very, very long design life to, I guess, maximize the return from the resource, which for renewables is never ending. But it also gives you a longer time over which you pay back the cost of the capital outlay, which we saw at the start is about something between 60 or 70% of the TOTEX. So what do you need to do that? You need to have appropriate specification of your facilities to achieve that design life, and you also need to have a reliable system so that it keeps producing for that design life. Design standards is one that is, look, in my experience, it kind of goes in cycles of everybody standardizing to what is specified by the D&B and the Lloyds of this world, to then we go through a phase of adding layer upon layer upon layer of company specific specifications, and then they get taken out again in maybe 10 years time. So I think the challenge here is to be very, very clear on what are the requirements on the equipment to give you the reliability needed. It's very easy to say, and I'm feeling a little bit kind of nervous just standing here saying that, because I've been through 2 or 3 cycles of where the whole industry says, yes, let's standardize and let's cut out the fat, and then it inevitably comes back. So maybe if I'm speaking to anybody in the wind industry, that's certainly one of the lessons that is a cyclical problem in oil and gas from my experience. JIP 33 is a more recent innovation or adaptation trying to get standardization across the industry. And if anything, what the renewables or what the wind industry is not, it's not the same as oil and gas, because oil and gas, inevitably everything is a bespoke project. But in the wind space, by definition, everything is the same. You have these, it's far more appropriate, or far more, I'm trying to think of a word. far more receptive of replication, industrialization, and standardization than an oil and gas project would be. This is one close to my heart, is system integration. You know, these are pretty, once you go to floating wind, you're talking about you're talking about large loads in a complex environment. And there's definite benefits in integrating and considering it from a mechanical design perspective as a system, not as a sum of components. If you want to have an over-designed and over-spec'd and inefficient facility, design it as a sum of components. So integrating your components into a single system, and then having a clearly defined system owner is definitely of benefit. And again, it's a learning we've learned the hard way. Like the classic one, I'll think back to my early 90s in the North Sea. We'd have one company would design the turret and the mooring, and then somebody else would design the riser system, and then inevitably there's an interface there. So we would over-design the riser system because the mooring system guys were over-designing there. And it was only when you brought them together you could see that you could get a real material saving in terms of either increased availability or reduced cost. So that's the example that stuck in my head for quite a while. And again, like I alluded to earlier in the piece, you know, there is a lot of innovation happening here. There's a lot of commercial, there's a lot of bright minds looking at new concepts to try and get a competitive advantage and get a foothold in the marketplace. Some of these are companies that we already know well, like SBM comes to mind. I'm sure there's a few more in there. So Wood has produced qualitative review of floating offshore wind concepts. I think that was published in April, and we're committing to reproducing that every year. And that I think it's good because it just shows it will show the evolution. Some of these will become big successes and some of these will fall away. But it'll be interesting in hindsight to look back and see which ones have made it and which ones didn't. And I think for me, the big one and one of the biggest learnings that we can take from oil and gas is the focus and the recent successes on reliability. So if, you know, that the whole design process focused on reliability, so predictable outcome, and, you know, I hope that we can translate the learnings, you know, because essentially subsea is all about you design it, you set and forget. It's so expensive to intervene and to change something out if something goes wrong. So the mindset has to be designing with reliability in mind. And for the floating wind facility, I think the biggest challenge there is probably on the dynamic cable and how we can get to a position of having proven, reliable, robust dynamic cables that last if we need extended life to take the average cost per unit energy down, then we need to have cables that are reliable a long time into the future. Oh, sorry, I've kind of gone ahead of myself there. But look, we got a lot of learnings. We got a lot of learnings from joint industry projects. That basically umbilicals, power cables, especially in dynamic environments, are very challenging. By their nature, the materials that you need to transmit the electricity aren't great in a fatigue environment or a moving environment. So, and there is no global standard just now or a design standard. So again, it reminds me of the early 90s for flexible risers, which is my kind of technical background. there was no standard, so every company had their own standard and every manufacturer had their own standard, and never the twain shall meet, and inevitably it led to either schedule overruns, cost overruns, or reliability issues. So we were fortunate enough to be part of helping to bring API Spec 17J to the table, and that was a collaboration driven by Shell. So I think we're at the same, it's history repeating itself. We're at the same stage in the cycle with regards to subsea cables, especially dynamic cables. And then the big chestnut, collaboration. I was thinking about what to say on this slide for before we got connected. And I think, you know, the question is what drives collaboration? And I guess what drives collaboration is mutual interest and mutual benefit. But I think to get that mutual benefit, you need maturity. And I think maturity of industry is probably what you need. So that's perhaps, I'm not trying to be flippant or arrogant, but I think that's perhaps the challenge that we'll see in the floating offshore wind with a, well, I guess there are quite a few new entrants, so maybe not the same level of experience in terms of seeing the downside of going it alone. So if we can, as an industry, help to explain the benefits of collaboration, that would be great. It would be a big contribution, but I think that's a challenge. That's a challenge, and I'm not sure I know how to resolve it. Innovation. Look, I think from an innovation perspective, we've seen a lot of that in oil and gas, and I guess with innovation comes a step change, and you know, as you move from fixed to floating, or you move to off the shelf. I'm thinking Gulf of Mexico now, when TLPs came in, and then you had spar and a truss spar and a cell spar, that those levels of innovation kind of opened up a whole new geographic area for exploration and production of hydrocarbons. So innovation in terms of floating wind, I guess there is a lot of innovation happening in terms of the hull forms that are being developed. How do you foster innovation? I think innovation is driven by the entrepreneurial type companies that see the opportunity and go for it. And then, okay, this one is quite maybe a North Sea comment in terms of supply chain. There's a debate in the report about fabrication, you know, UK fabrication, European fabrication, Asian fabrication, and how you the benefits or otherwise of that. I guess some of the challenges, design one, build many. I've seen that time and time again from an oil and gas perspective with FPSOs and FLNG, etc. But again, I do see a big difference between you know, every reservoir having different characteristics and therefore slightly different weight requirements, etc. to floating wind, where you need multiple units, and you know, I don't see a reason why design one, build many I don't see why, or I do see it working in floating wind. And therefore, design one, build many. In that build many, is that then where you're bringing in industrialization in your fabrication process and your installation process, and you can, by scale, reduced costs. This is on the same topic, is basically industrialization of the so either the fabrication process or the installation process. If you look at oil and gas, really what's happening is that the more sophisticated companies have more sophisticated vessels that are reducing the amount of human interaction and human intervention, moving to robotics. It's safer, it's more reliable. You get a more well, in theory, you get a more reliable outcome. And there's a company called Triumph Offshore that are now building a fleet of carbon neutral vessels, so that they'll run on battery power, and then when the hydrocarbon powered engines kick in, then they have a scheme for offsetting that carbon, so that I guess that'll all play into having a increased automation, industrialization, and decarbonization. Look, we've learned a lot in the I guess the last 5 years. It's been on my radar in how do you really drive down operations cost and have less intervention, or when you do need to intervene, or maybe when you do need to inspect, how do you do that in a cheaper way, in a safer way, with less emissions? So the use of AUVs, data analytics, artificial intelligence, these are all starting to come into oil and gas as being, they've moved from being outliers and great ideas 4 or 5 years ago to being pretty much mainstream now. So the rate of innovation in that space is to me quite impressive. So again, because we're starting from a base of having a lot of capability now. There's no reason why we can't build on that, and having your data twin, the analytics, so that there's a lot better appreciation of the condition of that facility, and how it's really what you want to do is you want to optimize the energy you get out of it, and make sure that you're monitoring the degradation of the components, and you can do most of that with a hands-off or a hands-free perspective. So I'm waffling a little bit there, but I think there is a lot that has happened in the last 5 years that if we can translate that across to floating wind, there are definite benefits to be had. I think we're on the second last slide, Quatra. Embodied carbon is a new concept to me. I've only kind of been introduced to it in the last 18 months. But really it's looking at, for the whole life cycle of your project. This happens to be more of an onshore project in the schematic, but in the whole life cycle of the project, what is all the carbon that is emitted? Or what is the embodied carbon in the life cycle of the project? So that's, well, that is going to become an increasingly measured and important metric for any project that we try to get up. So in conclusion, I would say that, look, we've developed a model for TOTEX, and we've run a whole load of sensitivities on it. Collaboration and innovation is, well, there's a lot that we've learned, that there's a lot of good practice that has been hard earned in oil and gas. I think quite a few of us on the call have an eye in the future to our future is not purely oil and gas. Our future is oil and gas and renewables probably, or maybe it's exclusively renewables. So there's a lot of value that we have in our collective knowledge base to translate into real value for the renewable space. There's a lot of proven ways to deliver technology and innovation and reliability. let's not lose sight of that. The cost analysis, to me, when I looked at it, there's no silver bullet. It's incremental improvements, and you need to compound those improvements to achieve the cost reductions that are really required to make floating wind a viable option for energy production. And in terms of further work that we need to do as wood, well, we need to maintain that annual floating wind technology review. We need to Australianize this work so that it's more relevant to the audience. Now, I apologize if it's slightly irrelevant from being UK centric. We need to launch that power cable GIP, and we need to launch this embodied carbon tool online. All right. So, and that brings us to a conclusion.